All right, so KSP here is the solubility product, as we were talking about last time. And that again is for things that are typically insoluble, like we talked about, for example, silver chloride. And as we talked about, even though things are technically based on solubility rules insoluble, everything basically has some degree of solubility. And in the case of these KSPs, they are mostly going to be here on the reactant side. We can still write an equilibrium constant, which is our products. And really with the KSP, because these reactions are always written solid to aqueous ions, pretty much the KSP is usually just the product side. There's usually nobody on the reactant side, as they're usually solids in this case. We do it the exact same way we do everything else with Ks, which means if we do have a coefficient or it breaks apart into, say, two ions, we do need to square it as well. So again, if we had PbI2, we would have Pb2 plus and 2I minuses. KSP will be Pb2 plus, and again, we would square it. So there's really kind of two types of problems we kind of talked about with KSP, which is you're just given really just the KSP value. You want to know either the molar solubility, which is basically the molarity, or you want to know the solubility in grams per liter. Remember, again, it is the molar mass that allows you to go from one to the other. We do an ice table, and we do it very much like the other ice tables we've done, except that we do use, actually, in this case, S a lot of times instead of X, and S does stand for the molar solubility. So when you do solve for S in the ice table, just like you would solve for X, that will give you the molar solubility of that particular compound. We could also use it to obviously figure out the ion concentrations at equilibrium of each of the ions. We also are sometimes given the actual solubility of a compound, and you could calculate the KSP from that. And to do that, you usually want to get it to the molarity, so whatever units of solubility they give it to you in, grams per liter, kilograms per milliliter, whatever it may be. You eventually want to get it to moles per liter for each of the ions, and then you can plug it into the KSP expression. You could also do an ice table for that so you don't mess up, which again is a common error that we talked about, that sometimes people will see like a 3 and then not realize they have to do multiply by 3 and also cube it still, or they do one and not the other. So again, sometimes with the ice table, you can kind of visually see that. We finished up, I think, talking about one of the three sort of things that affect solubility, and that is common ion is one of them. And the presence of a common ion will do pretty much what it does for everything else, like in buffers. Again, if we had a common chloride in this one, Le Chatelier's principle would shift the equilibrium to the left. And what that's going to do is decrease the solubility of that salt. It's going to keep it together, basically, and not allow it to break apart. And there's a big sort of decrease in sort of the solubility that you see in that. You work again that like a normal ice table. You just got to make sure, kind of like if you're going to do it with a buffer ice table, you have an initial on this side instead of a 0. Otherwise, obviously, you're not doing that. Any questions on that stuff there? All right, then let's talk about another factor that affects solubility, and that's pH. And pH is a really big factor that affects solubility. That's why when you do those qualitative analysis experiments, which dare I say we have coming up after spring break, group 3 maybe, I think, because we skipped 2, I think. A lot of those steps, as you may remember, have you make it acidic, make it basic, and so forth. And again, the idea behind that is it can very much affect the solubility of ions that are floating around in that solution. So the common ion does decrease solubility. If we have an insoluble base, it will be soluble or will dissolve in acidic solutions. And if you have an insoluble acid, it will dissolve in basic solutions. So for example, we take magnesium hydroxide, which appears to be basic there since there's hydroxide involved. And the KSP there for it is 1.2 times 10 to the minus 11. We do a little calculation, a little ice table here, 0, 0, change, plus S. plus 2s, again for the coefficient. At equilibrium here, we will have s and 2s. Again, our KSP in this case would be the magnesium. We would also take the hydroxide, and we do need to square it because of the coefficient that is there, and that equals our 1.2 times 10 to the minus 11. If we put our values in there, that's going to give us s times 2s that's squared equals 1.2 times 10 to the minus 11. Here, that's going to give us a 4s cubed. Remember, you do need to square the number, not just the letter, which is, again, a super common error people make. We're going to divide by 4 there to the other side. That will give us 1.2 to the minus 11 divided by 4. Gives us s cubed is equal to 3 times 10 to the minus 12. A little cubed root action there on each side. That's going to give us, and again, if you don't have a cube root button on your calculator, you could use your caret and do 1 divided by 3 in parentheses, and that will basically do the cube root for you. I'll try that. Let's see. 1 divided by 3 looks good. All right, so that's going to give us a x of, or an s of 0.001442. That is going to give us the molar solubility here. We are going to we're going to put that into, for example, the hydroxide concentration. So if I took that into the hydroxide concentration at equilibrium, it actually equals 2 times S. So if we take that value there, 2 times 0.001442, that will give us our hydroxide concentration, which would be, if I hit all the numbers before I hit equals, that would be good. Let's try that. There you go. It's almost right. 0.002884 molar. Now, why by earth would I want the hydroxide concentration? If I have the hydroxide concentration, I could calculate the POH, yeah, which would be minus the log of that number. And that would get me a POH here of, we'll call it 3.54. That would then give me a pH of 14 minus 3.54. And that's going to get me a pH of 10.46. So this solution of magnesium hydroxide has a molar solubility of 0.000142, and it has a pH of 10.46. So again, if you have something that's hydroxide, you have something that has H+, you can use this sort of calculation to figure out the pH of the solution. So sitting there in the beaker, this beaker should have a pH around 10.46. So let's say that I decided to lower the pH below 10.46. If I'm going to lower this pH below 10.46, I need to add what to it, an acid or a base? Probably an acid, right? So I probably need to add an acid, which is essentially adding H+. So what is going to happen in this case when I add H+ to this? It is obviously not in the equilibrium, right? But will H+ react with somebody there? I would say when you add that H+, the H+ and the OH- will then make water, right? And that will essentially be like removing hydroxide. And Le Chatelier's principle would tell us that the equilibrium then should shift to the right towards that way, and that will actually increase the solubility of it. This is an insoluble base. If you add acid to it, it's going to cause a shift in equilibrium to the right because you're removing hydroxide, and more of it will dissolve in this case. Yeah. By the way, do I need to make it completely acidic to do that? The answer is no. It could still be basic overall, but as long as it's less than 10.46, you will start to see that solid start to dissolve. So It doesn't necessarily have to get to an acid pH or acidic pH, but as long as that baseline, which is why it's important if you know the baseline pH of that solution is 10.46, if you take it down a little bit, it's going to start to dissolve that solid. Obviously, you go fully acidic is going to super dissolve that acid or that base in that case. Now, what would happen if we sort of did the opposite, which is we decided we want to go above a pH of 10.46. To do that, we obviously would probably need to add a base. And when we add base, we're essentially adding hydroxide in this case, right? And hydroxide is actually in the equilibrium. Hydroxide is still over here. And in this case, when we go and add that base, because we're adding more products, Le Chatelier's principle should cause the equilibrium to shift away from the side we added it to. So it would actually shift to the left. On the left-hand side, that is more solid, right? So in this case, we would actually be decreasing the solubility of it. We would see more solid occur. So you can look at pH, and pH is really important, even though, you know, for example, if we had something like this, which is supposed to be insoluble, but you made an extremely acidic solution, it won't come out of solution, right? It will basically stay in solution. You can keep those guys in solution floating around. If you then wanted it to come out of solution, you swap it to basic, right? And then you should start to see stuff dropping out of solution. And again, so playing with the pH is another way that we can affect the solubility of something. And again, like I said, sometimes you can actually calculate the baseline pH of that solution and figure out what would happen if you went above or below that baseline pH. Any questions on that there? So common ion can definitely affect it. pH obviously can definitely affect it. And one other thing that could really affect it is the concentration of the ions. And the concentration of the ions can also have a big effect as to whether or not you would see perhaps a solid form or not form. And this happens a lot, for example, in those qualitative analysis experiments where people kind of drop too much solution and go a little crazy with the solution and the water. Again, every time in those type of experiments, for example, you are adding a reagent, you're really diluting your sample. And in a true qualitative analysis experiment, which we don't really do too much of that anymore because they got rid of a lot of those, a lot of the steps that they used to have in there would be along the way, you would take your sample, put it on like a hot plate, and reduce down the volume and concentrate it back down, get rid of some of the excess water so that your test would actually work out. So it's very common if you add too much, you know, you may actually change the concentration to a point where you won't see that. And that's really what we talked about a little bit earlier on in the chapter, where we could compare Q to the KSP value. And again, if Q is greater than the KSP, we would expect a precipitate to form. Remember, these guys, again, are sort of solid to aqueous ions. So if Q is less than or greater than the KSP, it goes opposite of where it's pointing, so it should go towards the solid. And if Q is less than the KSP, it would go the opposite direction towards aqueous ions, and we wouldn't expect a precipitate to form. So why don't you try that here? If you mix together sodium hydroxide and calcium chloride together in these sort of concentrations and volumes, would you expect a precipitate to form? So the first thing you want to think about is when you throw those in there, we obviously have sodium ion and a hydroxide ion going for a swim from sodium hydroxide. We also have some calcium ions and some chloride ions. So you want to think about sort of your solubility rules to determine would there be any type of solid that would form in this case. Obviously, our choices would be these guys come together, and obviously those guys come together are our two sort of choices. So clearly sodium chloride, based on solubility rules, would you get a solid? I'm going to say no, since that's group one, and everybody in group one is quite soluble as well. So that's not the option here. So our option actually is calcium hydroxide is a possible solid that could form in this case. And what we want to know is basically, is the Q value greater than or less than the KSP? So the KSP for calcium hydroxide, if you looked it up in the table, would be 8 times 10 to the minus 6. So why don't you take a moment here and calculate Q and see if you would expect a solid to form. Okay, so let's take a look. So again, in this case, what we're looking to try to compare is Q versus the KSP. Again, Q is calculated the same way as our KSP. So since they gave it to us there, it would be our calcium and our hydroxide squared. We do want to make sure that since we are putting this all into like a beaker here together, the sodium and our calcium chloride, that we actually get the concentration when they come together and they mix. So that's a little M1 V1 equals M2 V2 action you could do here. Obviously, our source of hydroxide is going to come from the sodium hydroxide. So really the concentration of hydroxide in this case is going to equal our M1, which will go 0.2 molar. Our V1 is 2 milliliters. That's going to equal our M2 when they're mixed together. And because I use milliliters on my first volume and this one's in liters, I'm going to convert that to milliliters so everybody's on the same page. So that's 1,000 milliliters plus my 2 milliliters. That would give me a final volume of 1,002 milliliters, right? When we put it all together, that's going to go 0.2 times 2 divided by 1,002. That way everybody's in the same units. That's going to give me a hydroxide concentration of 3.99 times 10 to the minus 4. Obviously here, the only source of calcium is going to come from our calcium chloride. And we'll do the same thing here for our calcium. We'll do our, again, I'm going to use it in milliliters. So 1,000 milliliters, which is 1 liter, times our 0.1 molar equals our M2. And once again, same total volume here of 1,002. That gives me 1,000 times 0.1 divided by 1,002, or 10,002 if you type it in like I did. All right, let's try that one. That's going to give us a 9.98 times 10 to the minus 2 molar as our calcium. By the way, again, it is a 1-to-1 relationship as to how these guys break apart. So whatever this guy's concentration is, so is the calcium's. And it's also obviously a 1-to-1 relationship when this guy breaks apart between the sodium hydroxide and the hydroxide. So their concentrations, again, are the same in this case, right? Obviously, if it's not a 1-to-1, you just adjust it based on how many it breaks apart into. Now that we have our proper concentrations here, into Q we go. Q is going to be our calcium, which was 9.98 times 10 to the minus 2. Our hydroxide of 3.99 times 10 to the minus 4. Remember, we still got to square that thing. And that will get us a Q of 1.6 times 10 to the minus 8. Questions on that calculation there. Now that we calculated Q, right, we want to compare the Q value to the KSP value in this case. KSP value 10 to the minus 6, and our Q is 10 to the minus 8. That would mean that our Q is actually less than our KSP in this case. Would we expect to precipitate in this case? The answer is no, because it's going opposite, so it should go towards the product side, which means no precipitate. So again, an example of solubility rule says when we throw those guys together, we should get a solid, but because of the concentration of the ions that are floating around the solution, you actually will not see the solid in this case. So again, that's a really important factor in terms of whether or not you will see the solid form. So those three things, like I said, pH, common ion, and the concentration of the ions all have a major role in terms of solubility of salts and whether or not, again, they will stay dissolved or they will precipitate out. Question on that one there. Okay, we're going to continue on here. We're going to lecture and going to finish up chapter 15. And we're going to go on break, I think. And hopefully before Chipotle closes, right? So we get there before. All right. All right. So any questions so far what we've been talking about here? All right. So what are we doing here? There you go. All right. So next thing we're going to talk about, as we've been talking about sort of the things that affect solubility, we're going to talk about one of the aspects of KSP that can be very helpful. And we do see it in when we're doing sort of like qualitative analysis experiments. And this is an aspect of KSP that we could use to do what is known as sort of selective precipitation. So as you know, for your qualitative analysis sort of experiments, we have a bunch of ions that are floating around in the solution, and you add reagents to sort of selectively precipitate out certain ions from the solution and as precipitates and leave the other ones basically floating around. And we can use KSP to help us understand what level of, for example, of a precipitating reagent that we need to add to actually get just one thing to come out of solution first and leave the other one flowing in solution. So if we have, like in this example here, a solution that contains both bromide ions and chloride ions floating around, and if we wanted to precipitate these guys out by adding silver, like from something like silver nitrate to it, when we do, it will precipitate out as silver bromide, GBr, and silver chloride. Now, if you are not careful as to how you add the silver here in terms of its concentration, you will actually get both of them to precipitate out at the same time. And that can be really problematic because, as you can see from the picture, they kind of look the same. They're both kind of a white solid, which means you won't really know, like, I think this white solid crystal is like the silver chloride, or this one is the silver bromide. So there's really no way to know really which ions you sort of precipitated out. So in a situation like this, we may want to precipitate out just one ion at a time and try to get that guy out completely, and then go and precipitate out the other ion. So in this case, these are our two sort of options for solids that would be made here, our silver bromide and our silver chloride. And we want, in this case, to actually precipitate out only the bromide. So we want to add silver to take this guy out, but we do want to leave the chloride still floating around in the solution and obviously not a solid. So we could use KSP to help us with this. So if we look at the KSP expression here for our silver bromide, we have something like this. The silver concentration times the bromide concentration equals 7.7 times 10 to the minus 13. Now, we know in this case, even though I crossed it out there, that both of these ions are in the solution basically at a concentration of 0.02 molar. So we could actually rearrange the KSP expression and actually solve for silver in this case, which would be 7.7 times 10 to the minus 13 divided by the bromide concentration. And if we do that and we put it in there, that is going to give us here an answer of, we'll call it 3.9 times 10 to the minus 11. So I go down here, 3.9 times 10 to the minus 11 molar. So this number here represents the silver concentration that is necessary to first start to see the silver bromide start to precipitate out. So that is the minimum concentration of silver that you would need to add for it to react with the bromide and actually see, well, not necessarily a red solid, but a white solid sort of come out of solution. Now, we could do a very similar calculation for silver chloride and figure out the silver concentration that is needed to precipitate out the chloride. And we could do the exact same thing here. So our KSP would be our silver concentration times our chloride concentration, and that would equal our KSP value of 1.6 times 10 to the minus 10. Once again, we could solve for the silver concentration here, which would be 1.6 times 10 to the minus 10 divided by 0.02, which in this case is the chloride concentration. And if we do that, we see that to start to precipitate out the chloride as silver chloride, we would need something like 8 times 10 to the minus 9 molar. And that number of 8 times 10 to the minus 9 molar is the minimum amount of silver that you would need to add there to see silver chloride coming out. So by doing this calculation, what we can see is if we take the concentration of silver and we have it greater than 3.9 times 10 to the minus 11 molar, we will start to see bromide precipitate out as silver bromide. Now, if we keep that concentration less than 8 times 10 to the minus 9, we will see only silver bromide coming out. So if you were going to do this, what you would want to do is get a silver concentration. And again, if your silver concentration is less than 3.9 times 10 to the minus 11, you won't see a solid come out. So that's again back to what we were talking about a second ago. That concentration of everybody is really important as well. But if you get it to 3.9 times 10 to the minus 11 and you start dumping it into this beaker, you will start to see some white solid come out. And you can feel very confident at that point that the white solid that you see is the silver bromide that's coming out of solution. That is because you know that you need to get the silver concentration to 8 times 10 to the minus 9 to actually see chloride come out. So that's way less than that. So you could continue to add silver. You could even increase the concentration of silver as long as you keep it below 8 times 10 to the minus 9. And every precipitate that you see come out as you do that will always be silver bromide in this case, right? Because it's not enough to get the chloride out. It's still going to be floating around. At some point, what you probably will see is no more solid will come out, right? As you're adding the silver. At that point, you can then increase the concentration of silver to what we need to get the chloride out. And you can increase it to 8 times 10 to the minus 9 or above. And you will now start to see solid form again. And that solid at that point is going to be the silver chloride. And again, here, by controlling the concentration of the silver, we're able to selectively precipitate out both of those ions, basically one at a time, using actually the same ion to do so. We can use silver in both cases, but by controlling the concentration, we can selectively almost reach in there and just take out the bromide. And once that's gone, we could then increase the concentration of the silver and reach back in and start taking out the chloride. Question on that. What would happen if I just started and I didn't do any calculation and I just grabbed off the shelf some silver nitrate that had a concentration greater than 8 times 10 to the minus 9 and I just dumped it in there? What would happen? Everybody's going to come out at once, right? So that's enough to get the chloride to precipitate out. That's clearly enough to get the bromide. And you'd be in our original conversation we were having of you would just have a mess of solid there, not know which one's which. So again, you could kind of use KSP to your advantage to know sort of the concentration that you need, for example, of a precipitating reagent to precipitate that out as a solid. Any questions on that there? So that is, again, sort of what happens in qualitative analysis. Usually when you do those type of experiments, all those ions that are floating around that you're trying to precipitate out, it's actually usually in a concentration somewhere around 0.1 molar. And you have the right sort of concentration of your precipitating reagents to precipitate it out. Any questions on using KSP to selectively precipitate out something? Okay. As you know, this is basically about qualitative analysis KSP, and we have our different groups. Our group 1, which we already did. Our group 2, we don't do anymore. Yay. Our group 3 after spring break. I don't know which face you want, whichever one you want there. And then we got some 4 and 5 coming up there as well, which is a lot of flame tests. But As we were talking about when we talked about qualitative analysis in general, we do want to do this in specific orders. And again, these guys are related to each other based on solubility properties, not group one on the periodic table or anything like that. And obviously, there are precipitating reagents, as we know. As you saw in group one, HCl is a precipitating reagent for group one because that basically takes all these guys out as solid chlorides. Hydrogen sulfide gas is actually the precipitating reagent for, again, both group 2 and 3, which is good. They don't even use any sulfur anymore, so that's really good. But as you can see here, something we talked about a second ago, the difference between group 2 and 3 is they both use the same precipitating reagent, but the pH is very, very different in each case. We actually make it really acidic there for group 2, and what that does, because it's acidic from group 2, all those group 3 ions are going to be a lot more soluble, and they'll stay in solution, while those group 2 ions will actually come out of solution. Yeah.
pH was at 7, right? Nothing.
Yeah, so it depends on the concentration, and it depends on what is there in terms of if you're talking about group 2 or group 3. You could play with some other factors that might allow it to precipitate out, but ideally, definitely for the acidic ones, you do definitely need it to be acidic. And when we're talking about acidic, by the way, in this case, for group 2, which we don't do anymore, we're talking about like a pH of 0.5. That's like super acidic. So you have to drop a lot of acid there to drop the pH. You use that pH paper until you get to like 0.5 pH. So it's really, really acidic. And vice versa, when you get to group 3, as you'll see after spring break, you actually add a lot of sodium hydroxide and ammonia, and you get it really basic at that point. And that's again going to allow these guys now to basically drop out of solution. And usually if you do this in a general unknown situation, you're going from group 1 to group 2 to group 3, you've already made it really acidic at that point. So you have to add a lot of base to get it back to being really basic to get those guys come out. When we get to kind of group 4 and group 5, typically those are guys that are pretty much soluble in a lot of things. So we do a lot of flame tests with people, sometimes like or dislike, whatever it may be. We also have ammonia, which is soluble in everything. So there aren't necessarily certain tests that you could do for those. So flame tests and things of that nature are sometimes used. There are still a few like barium and calcium that you could still get a precipitate out. But we rely a lot on sort of flame tests, and potassium and sodium, as you may be familiar with. Sodium is that yellow flame that nobody knows if they have it, or it's just the Bunsen burner flame right when they start. And potassium is that kind of purple violet one. And if you have sodium and potassium there together, the sodium flame will block the potassium flame and you can't see it. And that's why we use those cobalt glasses that they put out in 200A, where we never use in their flame testing. But that's really why it's there, because it will actually screen out the sodium flame and allow you to see the potassium flame. If there is no sodium, you'll be able to see something like potassium with your naked eye. You'll be able to see the purple flame. But if the sodium's there, it will kind of block it and stuff like that. So that's always a fun one. People always call other people over and go, "Do you see it? I think I see the purple. Do you see the purple? I don't know. Maybe I see it." And that'll be used shortly here, a few weeks. All right. One more equilibrium thing to talk about here, which is for complex ion equilibrium. And a complex ion is usually a metal with a positive charge. A lot of times it's a transition metal, and it basically has what is referred to as a ligand attached to it. A ligand is a Lewis base, which you remember is something that will donate a pair of electrons. So a Lewis base is something that donates a pair of electrons. Like chloride, these are things that are negatively charged, which means they have electrons to donate. Water is also a very good Lewis base. So is our friend ammonia as well. It's a Lewis base as well. So things that are polar, that have non-bonding electrons, are usually things that can sort of be really good Lewis bases. Remember, Lewis acid is something that is electron deficient, which is like this guy. He's got a +2 charge. He's missing some electrons, which makes him pretty happy to accept some electrons over there from the chloride to form this complex ion that's over here. We can write an equilibrium constant for this, just like all the other ones, our products over our reactants. Here again, we still need to do our coefficient. This is what is known as the Kf added to our ever-growing list of K values. Kc, Kp, Kw, A, B, Sp, F, right? This class is brought to you by the letter K. So the Kf value is the equilibrium constant for complex ion formation. You actually did, not this one, but you did one earlier there in group 1. When you added the ammonia to your solid of silver and mercury, your silver dissolved, right? And it dissolved aqueously and it made a complex ion. And Kf value increases, the stability of the complex ion also increases. Again, a large K value means we mainly have products, and on the product side there, we do have our complex ion. Unlike KSP, Kf values, as we will see, are typically really large values. So KSP is really small because things are insoluble. Kf values are usually really large. And that is because complex ion formation, if it can happen, it will happen, basically. It is really favored a lot. And that's, if you just think about what you did there, you basically had silver chloride in a solid form. You added an ammonia to it, and it was able to rip that silver out of there and go combine with the ammonia, right? So it's that formation of that complex ion is usually fairly favored, and it usually has a pretty large K value associated with that. So some common ligands, as I mentioned, is water, ammonia, chloride, cyanide. Again, things with negative charges, things that are polar as well. Something we sometimes talk about with complex ions, and we'll talk about it more specifically when we get to that chapter a little bit later on about complex ions, is what's known as coordination number. And the coordination number is how many atoms are directly attached to the metal. So, for example, here in the case of cobalt, it is attached to 6 waters. I'm not going to draw it correctly. I'll just draw 1 correctly here. And 1 more. It is actually attached to the oxygen in this case, is how it's attached. And really, there's 1 oxygen, 2, 3, 4, 5, and 6 oxygens attached directly to the metal. And that would give it, if I go back there, that would give it a coordination number of 6. The cobalt here would have a coordination number of 4, and it basically is kind of the same idea. It's attached to 4 chlorides, and that would be the coordination number. Now, you might think that the coordination number is always just the number on the bottom, and the answer is no, it's not. And, you know, for example, as we will see, you could have oxalate, which is also a good Lewis base. If you draw oxalate, it looks something like this, if I remember semi-correctly here. I'm going to put the electrons on like I'm in chemistry class. There we go. And put a minus there. This is actually oxalate, and 1 molecule of oxalate, if you had a metal there, could actually attach in 2 places through each of those single bonded oxygens to the metal, which means if you had actually 2 oxalate ions here, this guy could also attach into. Coordination number here would be 1, 2, 3, and 4 would be the coordination number. Although you may see a formula that looks something like this, C2O42. And again, it would not equal that number that's on the bottom. So it does depend. There are ligands that attach in 1 place per molecule, which is known as monodentate. There are ligands that attach in 2 places, which is referred to as bidentate. And polydentate ones, they're ones that attach upwards of like 6 places. EDTA, if you look on labels, you'll see EDTA listed. It's like this guy that could grab a metal in 6 different places per 1 molecule. It just grabs it really, really well. Yeah. It is, yeah. So we'll go in more detail when we get into that chapter a little bit later on, but just a little preview of that there. Metals, though, which is important to sort of the calculation part, they actually do add ligands one at a time. So, for example, if we looked at the COCl4 there, this guy up here, we looked at the COCl4 2 minus. What happens is in this particular case, we'll hink the screen. There it is. Get rid of that there. Is that cobalt's actually going to accept each of those ligands basically in a stepwise fashion. It's very similar to how hydrogens are sort of lost in diprotic acids or polyprotic acids. So the first thing that would happen is the cobalt here, which has a +2 charge, would add just one chloride. And it would make COCl plus. And there could be a K sort of equilibrium constant for that step. This guy here would then pick up another chloride and make COCl2. There would be a K for that guy. We'll call it K1, K2. The next thing that would happen is this guy would then pick up his third chloride and make COCl3 minus. That'd be K3, we'll call it. And lastly, the COCl3 minus would pick up one last chloride and would make COCl4 2 minus, which is our complex ion there, which would be like our K4. So it does come on basically one at a time. Yeah. It's actually relatively easier. It's kind of a little bit different than that. It's not super hard to kind of keep popping these guys on. Again, the idea here is it depends really on the charge, as we'll talk about in that chapter. The charge of the metal determines really how many that they'll kind of pop on. So things typically with a +2 or +3 charge typically will get like 4 of them. Things with like a +1 charge typically will usually add like 2, and things like a +3 or a little bit higher will usually add like 6 or more type to it.
Harder to put on K3.
No, it wouldn't, because again, it's able to do that just to kind of make it a little bit more stable. So it definitely wants to put it on. It'll be okay in this case.
It's gonna get more negative.
Yeah, it's not necessarily super hard to do that, because the overall formation of how many they put on is definitely favored because you have a super large sort of K value for that. And this gives us really the overall sort of reaction that's taking place. If you add all these together, this cancels, this cancels, this cancels, and this gives us our overall reaction of how we put that on, which is one cobalt in, 1, 2, 3, 4 of these chlorides come on and makes our complex ion here, which is COCl4. So in these problems, sometimes you're given the overall reaction with the K value. Sometimes you may be given it in sort of a stepwise fashion, but that's okay. If I wanted the KF for this overall, how would I get it? What do I do with all these K values? We do multiply. Remember, we don't add them, so we have to multiply them. So it basically would be K1 times K2 times K3 times K4 in that case. So again, sometimes you are given it in a stepwise sort of fashion, and sometimes you're just kind of given the overall reaction with all 4 of them, for example, added in there. Remember as well, you can, if you needed to, use each of these individually because they are equilibrium reactions. They are K values, so you could just set up and write a K expression for each of the steps along the way. All right, so let's take a look here. Let's take a look at one together just to kind of show you a little bit of the difference in the type of calculation that we do with these. And in this case, we're going to take 0.2 moles of copper 2 sulfate is mixed with a liter of 1.2 molar ammonia, and we want to know what is the copper 2 concentration, the free copper 2 concentration at equilibrium. We're going to assume in this question that all the volumes will be 1 liter. So we don't always do that, and sometimes you do need to take into account the volume. But for this first example here, we're just going to assume that. So what that means is we're going to basically be mixing these guys together, and we want really our total volume here in our molarity. And in this case, we have 0.2 moles of copper 2 sulfate. This guy is going to be our source of copper 2, as that's the only copper involved. That means initially here we would have 0.2 molar. And in this case, we get that by assuming that our volume total is going to stay at 1 liter. So that would get us our 0.2 molar that we have for our copper in this case. Our ammonia is going to be our 1.2 molar. So we're just going to assume that it's going to stay at 1 liter. So basically, if you took 1 liter divided by 1 liter, they cancel out and it still stays at 1.2 in this case. And this is going to be 0. So we want kind of the concentration of everybody together. And again, in this case, we're keeping the volume constant, just to keep the numbers the same. Now, different than a normal ice table that we do here is when we look at the K value associated with this, the K value is a really large value, as I mentioned. And normally we would go through this, and I'll put it in blue here, and we would do our minus X, right? We would do our minus 4X because of the number there, and this would be our plus X, right? Now, when we do these type of problems, we make a couple of assumptions. The first assumption is that this value is really large, which means basically all of the metal in this case, which is really the limiting reagent, if you look at it, it's a smaller number, right? It's 0.2, is going to actually get used up. So unlike our normal tables where we kind of do it with X's when we're doing molarity, when we're dealing with complex ions, we actually just use the number because we already know what it's going to be. And it's always going to be the metal. The metal usually is always the limiting reagent in a complex ion. It's always a guy stuck in the middle that gets everybody else attached to it. So that is sort of always our limiting reagent. So instead of kind of doing our X's here, we would actually use the metal as our change. This would be minus 0.2. This would be minus, we still need to do it by 4 times 0.2. This would be plus 0.2. So that's sort of equivalent to our minus X's and plus X's in this case. Any question on that there? Yeah.
Essentially.
Yeah, so really the first assumption of these type of problems is because the K value is so large, that's going to force really the formation of the complex ion. And the complex ion basically has the metal in the middle, which means as soon as that metal is gone, you can't make any more ions because you have nothing to put in the middle, basically, right? So usually the metal should always be the limiting reagent in this case. That means that when we reach equilibrium, we should have 0 for our metal because that should be our limiting reagent. We would take 1.2 minus 4 times our metal, which would be in this case 0.4 molar, and we would have 0.2 molar. So first off, a little bit different of an ice table, kind of the same idea, except we kind of know the answer for our X in this case. Now, the question is actually asking what is the copper 2 concentration at equilibrium. And clearly in our ice table, we zeroed it out, right? Because it was a change, which means this wouldn't be much of a problem if that was the answer for all of these, right? So it is not. So even though we pretty much zero it all out with our first assumption, the second assumption is it is still in equilibrium, which means even though pretty much 100% of it is going to come over here, there's still going to be a little bit of it going back the other way, which means you should have a little bit of the free ion still in the solution. So the second assumption is we should still have a little bit of the free metal ion in the solution, but it should be really, really small number. So we should get a really small number for the free, in this case, copper ion or metal ion that's in the solution. So the second assumption is we should end up with a very small concentration of free metal ion. While first assumption is large, so the change is going to be the metal, right? So the way that we're able to do this is, even though we zeroed it out, we're going to kind of go back and go, okay, now we actually want to solve for it. And the way that we could solve for it is to actually just use the equilibrium constant. So we could use the Kf, and the Kf in this case is CuNH3 to the fourth divided by our Cu2 plus and our NH3. And again, we still need to take it to the fourth power because of the coefficient. And that's going to equal 5 times 10 to the 13th. At this point, we would put all of our numbers into our expression. So we would have 5 times 10 to the 13 equals 0.2 divided by the copper, which is what we're looking for, and divided by 0.4 to the fourth. Mathematically speaking, multiply one to one side, divide by the other. These two guys end up switching places, basically. Is what you end up there. You multiply the copper 2 to the other side, and you divide by the 5 times 10 to the 13, and you end up with this 5 times 10 to the 13. Those guys just switch places and are 0.4 to the fourth, basically. So if we put that in now, we get 0.2 divided by 5 to the 13 divided by 0.4 to the fourth. That's going to give us a copper concentration at equilibrium of 1.6 times 10 to the minus 13 molar. Is that a large value? No, that's pretty much, it's all gone, right? There's like a trace of it left somewhere, not very much. So again, that fits our assumption that we do here. If you get to this point in the calculation, you get a large number for the metal, you did something wrong. Yeah, for sure. So it should be a really, really small value. I would say in most cases, that would be definitely wrong. Any question on that? So kind of the same idea, except here the metal's going to be the change. And again, we're then going to zero out the metal, come back basically and kind of solve for it. Any questions on that one? Yeah. Okay. Other questions? Good question. I like it. All right. Is that all right? So let's try one here. It's a little bit different. This is a stepwise formation. So why don't you give it a try and see what you come up with? Here, we're not keeping the volumes constant, so you got to take that into account. You want to get the concentration of everybody. This is a stepwise formation here of this and this, and we want basically everybody's concentration along the way. So we're going to mix 150 milliliters of 1 times 10 to the minus 3 molar silver nitrate. I'm assuming that's my silver concentration there. With 200 milliliters of 5 molar Na2S2O3. And that would be my thiosulfate type of concentration, I think. All right, so give it a go. Complex ion. So there are a couple of approaches that you could do. One good approach might be just to add these reactions together to get our overall reaction. Just like anything else, anything that's on opposite sides that's the same could cancel out or reduce. So really this guy cancels. And that gives us really our equation here of our silver plus 2 of the S2O3 2 minus will form our complex ion here that we get over here. Now, again, if we wanted the K value for this guy here, we basically can multiply our 2K values there, and that would get us something like 7.4 to the 8 times 3.9 to the fourth, and we'll call it like 2.9 times 10 to the 13. First up, any questions on that part of it? All right, now that we're kind of making this complex ion, which is really what we're looking at, is this formation of the complex ion at the end, We do really want the concentrations of everybody that's been kind of mixed together. Again, we're not keeping our volumes constant in this case. So once again, a little M1 V1 equals M2 V2 sort of action would be good. Here, the silver nitrate is going to be our source of silver. So in this case, our M1 is 1 times 10 to the minus 3, it looks like. We're going to use 150 milliliters of it equals M2. And now we really want the total volume when we put them together. So we got 150 and 200. So that's going to give us a total volume here of 350 milliliters, which in this case would be our V2, right? Solving for M2 is going to give us a concentration for our silver, 1 to the minus 3 times 150 divided by 350. Go with 4.29 times 10 to the minus 4 molar. We will do the same thing for S2O32 minus. This sodium guy right here is going to be the source of that. And we're going to get the concentration when we kind of put everybody together. In this case, we have 5 for its molarity. We're going to use 200 milliliters of it, and it's going to go for a swim with everybody else. So we'll end up with 350 milliliters of it like normal here. And that will get us our concentration there of 2.86 molar in this case. Any questions on that there? So since I did actually get the overall reaction here, and essentially in this problem, we're looking for everybody. So we're looking for everybody in the kind of both of those steps, and even at the end there, I could use the overall equation to do my calculation to begin with. So that's what I'm going to do here. I'm going to use the overall equation that we just got, which was the silver plus our S2O32 minus, making our complex ion there. And again, this is the overall reaction here. We're going to use our initial concentration of our silver we just calculated, which was 4.29 times 10 to the minus 4. We're going to use our initial concentration of our S2O3, which was 2.86. And since this is a complex ion, right, we know that our first assumption is all of the metal, right, should get used up. And that's going to be our change here. So our change, once again, will be our metal, which is always the case in these type of problems, pretty much. This guy over here, there was a 2 here, right? So I should probably put that 2 would probably be good as well. So that's important right about here because we do need to take 2 times that value, right, of 4.29 times 10 to the minus 4. And over here we have plus 4.29 times 10 to the minus 4. Any questions on that table there? I did have the 2 on that side. That's good. That means when we reach equilibrium, we will have 0 of our silver like we anticipate. We will end up with, I think it's still 2.86. So let me see here. It's 2.86 still. And this is 4.29 times 10 to the minus 4. Any questions on that table right there? This table right here actually gave us 2 answers that we're looking for, right? We now have from this actual table, the concentration of our S2O32 minus is 2.86. We also have the concentration of our complex ion in this solution, which is 4.29 times 10 to the minus 4 molar. So at this point, if we do want to find some other things, we basically just found this guy, and we actually found this guy's concentration as well. So we're still looking for really these 2 concentrations. So at this point, you really do have a couple of options to do it. So one option is you could actually just use the stepwise equations. And if you look at the stepwise equation, the second one I have this guy's concentration from the table above. I also have this guy's concentration from the table we just did. So we could actually, at this point, if you wanted to, just use the K2 reaction and solve for this guy's concentration, which is one of the things we're looking for. So that's what I'm going to do here. I'm going to use the second step here. And the second step would give me an equilibrium expression of K, I'll call it K2, right, is equal to 3.9 times 10 to the 4. And that equals our product, which is our complex ion. Divided by this guy here, which is one of the things we are looking for. And our S2O32 minus. Now you may be asking, shouldn't that be squared? And the answer is no, because I am not using the overall reaction here. I am using this equation, yes? And there's only one in that case, yeah? So again, because we're using the second step, that's also why we're using the second step's K value as well, right? So we're not using the combined K value that we got originally. We're not using this one as it just popped up there. We're using that one. Once again, here we have these numbers from the table above, 4.29 times 10 to the minus 4, divided by this guy's concentration here, which is what we're looking for. And this guy here would be 2.86. Once again, our K value and this guy are basically just going to switch places as you multiply that guy to the other side and divide by the K value. And that's going to get us here that the AgS2O3 minus concentration equals 4.29 times 10 to the minus 4 divided by 3.9 times 10 to the 4 and 2.86. Just making sure it wasn't getting louder as it was coming closer. 4.29 to the minus 4 there. Divided by 3.9 to the 4 divided by 2.86, and that's going to give me something, with a lot of zeros, I suppose. I'll go scientific notation for, chemistry purposes. 3.8, we'll go with 4. 3.84 times 10 to the minus 9 molar. Yeah. First off, any question on that one there? Now that I actually have that concentration, you actually still have two options as to how you might want to do it. But since we already used the stepwise formation number 2, why not use number 1 at this point? Because now we have this number from our calculation we just did. We still have this guy as well. So we could actually use step number 1 now to actually find our silver that we're interested in. Well, so if we go now to the first step here, we could write the equilibrium expression for our first step, which would equal 7.4, a lot of glare, times 10 to the 8. And again, we're going to write our equilibrium expression for the first step, which would be our guy we just solved for, divided by our silver, which is what we're looking for, and our S2O32 minus. Again, putting in our numbers that we have, which is 3.84 times 10 to the minus 9, divided by our silver and our 2.86. Once again, we do not need to square it because, again, it is only 1 here in this reaction. Once again, this guy and this guy are going to switch places, basically. So I'm going to flip the page, I think, and do that there. So we'll go and do that there. That's going to give us that the silver in this case will equal our, I think it was 3.84 times 10 to the minus 9 divided by our 7.4 times 10 to the 8. and our 2.86, I think. So we're going to go that divided by 7.4 to the 8 divided by 2.86. Going to give us for our silver 1.8 times 10 to the minus 18 molar. Our second assumption when we do these problems is the metal ion should be large or small number. Is that a small number? It is, so that's good, right? So as you can see here, you could use each of the individual steps and calculate what you need because they're all equilibrium steps, which means you have an equilibrium constant. If you got equilibrium concentrations, you could go in there. Now, just to show you that if you wanted to attack the silver here after the first ice table, you could have done that with our combined value here. So you could have, after that first ice table, you could have used the KF that we calculated and went the KF would equal our complex ion divided by our silver and S2O32 minus squared in this case because we're using the overall reaction. And this would equal our 2.9 times 10 to the 13. Putting in our numbers from the first table, which I believe was our 4.29 times 10 to the minus 4, divided by our silver and our 2.86 squared equals 2.9 times 10 to the 13. Again, these guys are going to switch places, and that would give us a silver concentration of 4.29 times 10 to the minus 4 divided by 2.9 times 10 to the 13, and our 2.86 that we do need to square. And hopefully we should end up with the exact same number we just got. Otherwise, a little embarrassing if it isn't, but hopefully it is. There we go. 1.8, dare I say, times 10 to the minus 18. So you absolutely could have, like we did before, used the overall reaction and hit the silver. At that point, you could then go into whichever one you like here to solve for the other thing that's missing as well. So that's perfectly fine as well. Any questions on any of that there? All right, now the thing that you've waited for, which is the last example of the evening, is we're going to calculate the molar solubility of silver chloride in 1 molar ammonia. This is pretty much what you did in group 1 at the very end there. I was talking about where you added the ammonia to your solid. We're going to go through this together to see how it all works. So we're going to, why not, add these equations together to see what we got going on. So when I add these equations together, the silver ion oddly goes away. And we are left with really what the question is asking, silver chloride plus a couple of ammonias gives us our complex ion, which in a later chapter you'll be able to properly name. And some chloride moving around, right? Now, if I want the K value for this, is it okay to multiply a KSP by a KF? Is that okay? The answer is yeah, it's okay. It don't really matter, right? You did a KA times KB to get KW. Why not? Huh? They're all K values, so it doesn't matter that they're different little symbols on the bottom. So we can get the overall K value here, which in this case is 1.6 to the minus 10 times 1.5 to the 7. That's going to give us a K value of 2.4 times 10 to the minus 3. This is actually, in this case, although there's a KF involved, this is a KSP type problem, right? Because we're looking for the molar solubility, right? So that is what we want to approach here in this ice table is really more of a KSP type of problem rather than a KF type problem. Also, you can see that the combination of those two gives us a K value that's relatively small there, right? So it's not a sort of giant K value. So we're going to take the overall reaction here and we're going to work with that, which is again right there. Thank you. That is our silver chloride plus our 2NH3. Again, giving us our complex ion and our chloride here. And of course, we just got our K, which is 2.4 to the minus 3. 2.4 times 10 to the minus 3. All right, the only number we're given is we got 1 molar of ammonia. So when we go to our ice table, that looks like the only one that we got going on in this case. This is going to be 0 and 0. Once again, remember here, we're actually looking for the molar solubility. So we're going to do our normal sort of situation, which means this, which we don't normally have, is actually in play because that's ammonia, right? And not a solid. That's going to be minus 2s, right? Just like we have there with our coefficient. This will be plus s and plus s on this side. That's going to give us at equilibrium 1.0 minus 2s, s, and s. Any questions on that there? This is going to go into our equilibrium expression, which in this case is still our products. Over our reactants, which is NH3, and we do need to square it, right? So putting in some numbers here, that is going to give us an S times an S divided by 1.0 minus 2S squared equals our combined K value. So we want to solve for S here. Which way should I solve for S in this case? Big old square root looks like a nice, easy way to do that. That is a perfect square on each side. Why not take it here right before spring break? Right, there you go, 1.0 minus 2s. We also don't want to forget we should square root that last side there, 2.4 to the minus 3, and get an error. Try that again. There you go. Might learn how to use a calculator one of these days. Minus 3, there we go. That's going to give us a 4.899 times 10 to the minus 2. We're going to multiply this to the other side. That's going to give us S is equal to 4.899 times 10 to the minus 2 minus 9.798 times 10 to the minus 2s. We're going to combine over here, I think. So we're going to bring this to the other side to combine our s's. Can't go out of scientific notation. It's hard to look at. So we're going to add 1 to that, by the way. So that is a 1, right? I think in that case. So that's going to give us, so it's 1.098 equals 4.899 times 10 to the minus 2. We're going to divide, hopefully. 4.899 to the minus 2 divided by 1.098. That is going to give us an S of 0.0446. And that would be our moles per liter of our silver chloride in this case, right? Now, if we take silver's molar mass, which I remember is 107.9, I think, plus 35.45 for the chlorine. If I could find the right button, that would be great. There it is. That's going to give us a molar mass for silver chloride, as we did earlier, 143.35 grams per mole. So we'll times that by 0.0446. That's going to give us a whopping 6.39 grams per liter of silver chloride. Does anybody remember what the grams per liter of silver chloride solubility was in water? Something like 0.002 grams per liter. Yes. Which one is it more soluble in? Right there, I think, right? It's do I have it? Nope. Come back. So I think it was vaguely, if I remember, 0.002 grams per liter in water. Which one is it more soluble in? Definitely in the complex ion, yes. And that is why you're able to, when you did that experiment in group 1, when you added the ammonia, to pull that silver out of that chloride, because as soon as that silver finds that ammonia, is going to want to come together to form the complex ion, because the formation of complex ion is definitely favored. By the way, out of curiosity, why did the silver chloride come back? You hit it with a lot of acid, right? Got rid of this guy, frees up the silver again, and looky who's still there. Those guys then come back together to make the white solid that you saw in the fume hood, or the fumes and the white kind of stuff that kind of appeared in your test tube. And that's why your silver chloride comes back in that test. So this problem is actually what you did in group 1 to confirm